The following report will investigate the processes involved in designing the structural members of a domestic shed located in Australia. Each structural member will be analysed and discussed to ultimately determine an adequate design solution for each member. The members being investigated are purlins, side columns, rafters, bracing layouts, and bracing elements. Footings, floor slabs, earthquake design, as well as connection design would not be included in the investigation. However, all the connections will be pin ends as per the project specifications. Industrial are found in many forms such as portal frames, sawtooth frames, and space frames. The shed being investigated throughout this design project features a flat roof with a small pitch of 2 degrees, as well as a relatively small span of 4 meters. Hence, it will not require the amount of struct that many other larger industrial buildings do. Shown here are a few photographs taken from a recent site visit to the University of South Australia's Mawson Lake campus. This site visit involved observing how certain structural members behave when under load. The graphs below show the framing of a typical portal frame structure. Steel columns, rafters, girts, purlins, and bracings can all be seen in the building. These are the members that the following report will be examining and ultimately designing for use in a domestic shed. Throughout the report, the various loads that a domestic shed will be subjected to will be identified and investigated. Loads such as dead load, live load, as well as wind loads will be taken into consideration in order to design the structural members of various engineering practices will be employed to ultimately design a shed that can adequately withstand the forces that it will be subjected to, whilst also trying to utilize economical design methods to reduce the project costs. To determine the wind loads that the domestic shed will be subjected to, Australian standards must be used. As shown in Table 1, the domestic shed complies with the limitations of AS 4055 and therefore will be used to calculate that will be placed upon the shed. Outlined in Table 2.1a of AS 4055 is the design gust wind speed for non-cyclonic regions. This table identifies the wind speeds that the shed will be subjected to. However, first the wind must be found in order to determine the wind speed values. To establish what wind class the shed falls under, the region, terrain category, topographic class, as well as shielding must be found. This information was provided in the design parameters on Table 2. Table 2.2 in AS 4055 outlines which wind class the domestic shed falls under based on its wind region and other site conditions. It can be seen from the above table that the shed falls under the N3 wind class. This information is known. Table 2.1a of AS 4055 can be referred to in order to determine the wind speeds that the shed will be subjected to. It can be seen that the shed will be subjected to gust speeds of 32 meters in the serviceability limit state and 50 meters per second in the ultimate limit state. The serviceability limit state refers to factors such as stability, vibrations, and deflections, whilst the ultimate limit state refers to the strength factor of the structure.
Purlin design. Prior to designing the purlins, a roof sheeting material must be chosen. According to the project design parameters, this cladding is to be lysite trim deck. Load combinations for ultimate limit state. The critical load combinations for the purlins can be calculated using the formulas provided in AS 1170. The most critical load combinations are 1.047 kilopascals in a downward direction and 1.427 kilopascals in an upward direction. From here, the load per length of the purlin must be calculated. Therefore, the loads are 1.466 kilonewton meters in a downward direction and 1.998 kilonewton meters in an upward direction. One row of bridging is required for a span of 6 meters. The capacity of a Z219 purlin has an inward capacity of 2.81 kilonewton meters, which is more than needed, and an outward capacity of 2.26 kilonewton meters, which is also more than needed. Girt design. Designing the girts requires the same process that was utilised when designing the purlins. The only difference is that the wind pressure on the walls must be calculated. The walls of the shed will feature the same cladding as the roof, and it will also have the same insulation as found on the roof. Load combinations for ultimate limit state. The most critical load combinations are 1.45 kilopascals in an inward direction and 1.09 kilopascals in an outward direction. From here, the load per length of the girt must be calculated, and this has a value of 4.35 kilonewton meters in an inward direction and 3.27 kilonewton meters in an outward direction. Bridging. One row of bridging is needed. The test girt has an inward capacity of 5.24 kilonewton meters and an outward capacity of 5.24 kilonewton meters, which are both greater than the required values. Therefore, C250-24 is inadequate for the ultimate limit state. Roof bracing. X-direction roof bracing. Forces of intermediate frame are 14.175 kilonewtons of pressure and 12.128 kilonewtons of suction. Forces of the end of the frame are 7.088 kilonewtons of pressure and 6.064 kilonewtons of suction. Design roof bracing. Members that are under tension will be designed using an equal angle, and the members that are under compression will be designed using a square hollow section. The diagonal members require 41.08 kilonewtons of tensile strength and will be designed with a 150 by 150 by 19 equal angle. The struts require 38.97 kilonewtons of compressive strength and will be designed with a 75 by 75 by 4 square hollow section. Y direction roof bracing. Forces of intermediate frame are 4.725 kilonewtons of pressure and 4.043 kilonewtons of suction. Forces of end frame are 2.363 kilonewtons of pressure and 2.021 kilonewtons of suction. Design roof bracing. The diagonal members require 5.41 kilonewtons of tensile strength and will be designed with a 50 by 50 by 8 equal angle, and the struts require 6.72 kilonewtons of compressive strength and will be designed with a 65 by 65 by 1.6 square hollow section. X direction wall bracing. Lateral load. The lateral load is applied to the vertical truss that is equal to that of the reaction of the horizontal truss. Therefore, the load is equal to 8.768 kilonewtons. The diagonal members require 10.15 kilonewtons of tensile strength and will be designed with a 75 by 75 by 10 equal angle. Y direction wall bracing. The lateral load applied to the vertical truss is equal to 26.304 kilonewtons. Design wall bracing. The diagonal members require 52.22 kilonewtons of tensile strength and will be designed with a 200 by 200 by 18 equal angle. The struts require 46.03 kilonewtons of compressive strength and will be designed with a 65 by 65 by 2.5 square hollow section.
Purlin design requires all the loads applied to the purlin to be calculated. Dead load, live load and wind load must all be considered. Shown on screen are the calculated dead loads. These loads were then summated together to determine the maximum and minimum dead load. This is because when the purlins are subjected to suction, the minimum dead load must be considered. However, when the purlins are subjected to downward pressure, the maximum possible dead load must be considered. The Australian Standard 1170.1 must be referred to in order to calculate the live load that the purlins will be subjected to. Table 3.2 in AS 1170.1 provides reference values for roof actions. The live load subjected to the purlins can be calculated as shown on screen. The next stage of purlin design is to calculate the critical load combinations using the formulas provided in AS 1170.0. Shown on screen are the load combination calculations. It can be seen that the most critical load combinations are 1.074 kilopascals downwards and 1.427 kilopascals upward. From here, the load per length of the purlin must be calculated. The spacing between purlins is 1.4 meters. Therefore, the loads acting on the purlins are 1.466 kilonewton meters downwards and 1.998 kilonewton meters upwards. Bridging enhances purlin performance. When used correctly, it can result in a smaller and perhaps more economical purlin section being used. The capacity tables are then referred to check if the test purlin is capable of sustaining the required loads. It was found to be inadequate and hence a larger purlin section was selected. The larger purlin was capable of carrying the loads. The next step is to determine the new self-weight of the purlin and then ensure that it can support the new dead load. The serviceability limit of the purlin must also be considered in the design process. This is to ensure that it does not deflect too much. By using the serviceability limit state criteria outlined in section 4.3 of AS 1170.0, these load combinations can be used to determine the critical load. This load must then be checked against the capacity table to ensure that the purlin is up to the required performance. Rafters are horizontal beam members which transfer the loads from the purlins into the columns. Rafter design follows the same fundamental procedure as purlin design. The dead load is calculated using the same values that were used in the purlin design. The dead load summation for the rafters can be seen on screen now. Much like the process utilised in the purlin live load determination, Table 3.2 in AS 1170.1 must be referred to. This table provides the reference loads for roof actions. This value obtained is less than 0.25 kilopascals minimum required in the Australian standard, therefore it cannot be used. Instead, the 0.25 kilopascal value must be used as the value for live load on the rafters. Once again, the critical load formulas are then used to determine the critical load. The critical load is then multiplied by the spacing between the rafters to obtain the load per rafter length. The critical load combinations are then substituted into the bending moment formula to see if the test rafter can support the loads. Fly bracing helps to restrain the bottom flange of the rafter and reduce its effective length in the event of suction. This in turn increases the effective strength of the rafter. The capacity tables must then be checked to ensure that the member can sustain the forces applied. For our shed, a 150 UB18 beam was selected. Serviceability must also be checked. The critical load is obtained from the load combinations. The deflection formula must then be used to calculate the deflection in the beam. The maximum allowable deflection is 16 mm and hence is more than the 6.45 mm experienced in the rafter. This means that a 150 UB18 rafter is acceptable for use. Columns are vertical members that transfer the loads from the rafters into the footings. Exactly the same procedure is used to calculate the dead load for the column. Additionally, the live load calculation also follows the same procedures. The formulas in section 4.2.2 in AS 1170.0 can now be used to determine the critical load. The critical load is multiplied by the tributary area of the column to determine the load that the column will support. The design capacity tables must be checked to determine the column member size. The strength about the column's y-axis must be checked, as this is the member's weakest axis and is most prone to buckling. A 100 UC 14.8 column was found to be sufficient. The 100 UC 14.8 column must now be checked for its bending capacity. It can be seen in the table that a 100 UC 14.8 member has a moment capacity of 13 kilonewton meters and is less than the 0.64 kilonewton meters being applied to it. Hence, it is okay in terms of its moment capacity for the shed. The capacity of the 100 UC 14.8 member has been checked for its compression and moment performance separately. However, the member must also be assessed for its capacity to handle both of these loads together. The final column design step is to check if the 100 UC 14.8 member is capable of supporting the tensile forces it may be subjected to. Although this member is capable, it is extremely uneconomical as its capacity is substantially larger than what is required for the shed. Hence, a universal beam should be used instead of a universal column, as this will allow for a smaller section size.